Welcome back, everybody. Now we are going to start yet another section, but this is where it becomes interesting because in the first few weeks, I've told you a lot of layers like how to store data, how to map some models to syntax with XML, JSON, CSV, how all of these can be parsed as trees in the memory, how to validate it to enforce specific structures, even to the point that you can turn the data into data frames. And that's what we have done, right? We're already half through, and that's the first half of the semester. So this is a good milestone, right? And now this is where things start to be exciting because now we are going to actually start processing the data. And in order to do that, there is an experiment. I will not do it here, but I do it with my master students in the fall edition of the big data lecture, is that I come to the lecture with Pokemons, hundreds of them. What I want to do with the Pokemons is I want to count them. How many Pikachus, I want to have the counts. I could do it myself, counting them one by one, organizing them in piles and so on. So of course that would work, but it would take a lot of time. So in order to get these numbers, I thought maybe I can just ask my students to do it for me because we have the benefit of parallelism in the lecture hall, right? So different people can work on their own Pokemons at the same time. And so what I do is that I prepare these batches, these sets of Pokemons in advance. 10 of them, yes, 10 groups of Pokemons, and I ask for 10 volunteers, 10 students, who each get one of these groups. Let's call them batches. We'll see that the term for that is splits. These are technically splits, 10 splits. So I asked for 10 people to each take one split. And these people are supposed to look at what they have in their bag and to count locally, just for what they have, how many Pikachus and so on, right? And so they are supposed to write down the numbers. So I give them a piece of paper where they already have the distinct Pokemons and they have to write the numbers. Is everything okay? Oh, you're kicked out of the meeting. Yeah. For a moment, I thought that the microphone was not on or something, but let me accept you again. Yep. Thank you. It's very important that I do that because otherwise there might be people who would be waiting outside of the meeting. There you go. Yep, now you're a co-host again. All right, thank you for letting me know. So yes, these 10 students are supposed to count. They get a list of distinct Pokemons and they should put the number, the count that they find for each Pokemon in there. That is the end of the first phase, which is known as the map phase, as we will see. And then I ask for more volunteers, 8 people. Each one of these volunteers is going to be assigned responsibility for one Pokemon or 2 Pokemons, for which they need to prepare the final number, right? So this is also known as reducing. So these people are known as mappers and these as reducers. And something needs to happen in between is that the mappers, so the students who did the phase 1, need to cut these sheets by distinct Pokemon, so to cut them into separate Pokemons. And they need to distribute the strips of paper to the appropriate person. So in that case, this person, let's say Alice, who is assigned Pikachu, is supposed to receive the Pikachu strip from every one of the 10 students who did the map phase, right? Once Alice has all of her Pikachu strips, she can compute the sum of this and write it down on a new piece of paper, and then I get that piece of paper, and at the end I get back all of the counts from the reducers. Who agrees that we successfully counted the Pokemons in this way? Right? It works. It's simple, right? We count in parallel and then we add the counts. Well, it turns out that this is MapReduce. This is a human live MapReduce, but this is what we are going to now study in this lecture. Except that, of course, it's not always going to be with Pokemons. It turns out to be very generic. Just so you have a visual, while it happens, normally it's when it's in a data center, but here I did it at the same time that it was going on live, you can have this kind of visuals that you can process the evolution of the mapping phase. So basically with some progress bar that as people start counting the Pokemons in phase 1. And so you can have a first color and then a second color, that would be the shuffling. That's when they start handing over the strips from the mappers to the reducers, that you see the progress of handing over the intermediate strips, like this. And finally, you have the last phase, the reduce phase, when the Alice and her colleagues basically count. I cannot do it too fast because the screen flickers if I do it too fast. So I'm doing it slowly, but yes, these are the progress bars basically. And now we are completely done with the MapReduce. And some systems have progress bars like this while a MapReduce task is being carried out. Yes? So the initial progress bar is the mapping, the second one is the shuffling, and the third one is the reducing. So I don't think I have pronounced the word shuffling yet, so I will explain what shuffling is. Shuffling is when every student who volunteered for phase 1, for the map phase, hands over the strips to the students responsible for phase 2. That's called shuffling. In order to understand why it's called shuffling, you have to understand that at that point, the lecture hall is an enormous mess. Like students are just standing and walking around and walking to each other and looking for whom to give the strip to and so on. It's a huge mess. The algorithmic complexity for that is quadratic. And the reason that is that every mapping student has to meet every reducing students. So if there's 10 mapping students and 8 reducing students, that's 80 meetings, right? 80 times there needs to be 2 people who exchange the Pokemon strips, right? Who sees that? Right? And that's called shuffling because the Pokemon strips are just being shuffled around from the mappers to the reducers, right? So this is why it's called shuffling. And even though the algorithm is known as MapReduce, I think it would maybe have been more accurate to say map, shuffle, reduce than MapReduce, and this is why we have the 3 parts in the progress bar, but probably map, shuffle, reduce is less good for marketing, so MapReduce is kind of easier to pronounce. Does it answer your question? Right? So shuffling. All right. Now, of course, we are not going to do it with Pokemons and human beings. We are going to do it with computers. And the Pokemons are not going to be printed on paper. Instead, we are going to have data that is stored somewhere. Where? Well, we know where because I told you a lot of possibilities with the way we can store the data, right? For example, the data could be on HDFS. We could have plenty of files on HDFS. Maybe this data is text, right? Maybe you have all the Shakespeare works or the, I think that's Sir Arthur Conan Doyle, I think. That's Sherlock Holmes, the first Sherlock Holmes. So you could have like plenty of text, plenty of books that you want to process in some way. I'll give you examples of the sort of things you can do with that. So it could be text. Imagine billions, if not trillions of lines of text on HDFS. Or maybe I have text that is in the CSV format. So maybe I have billions or trillions of lines of CSV, comma-separated values. Now you see, because of the lecture I gave you earlier, you see that this is a relational table, a data frame, a flat data frame with 4 columns, year, date, duration, guessed. The first column is an integer, the second column is a date, the third column is a time, a duration in hours, minutes, seconds, and the fourth column is a string with optionality for the second, third, and fourth column. So you have null, null, null in 2020, right? These are the Zarcy-Luther dates with the time it took for the bug to burn down. So CSV files, that's the second thing you could have, or raw files. That is particularly popular with meteorology, like Meteo Suisse, gathering data from sensors and so on. Very often, it's very highly compressed. There's not even any commas in there. You just store the data like this. Why don't we need the commas? Well, we don't need the commas because this is when the data is so structured that the number of digits is always the same. So you don't need the comma here because you anyway know that these 4 digits are for the year. You know that this is a date. So this is again because the format of the data is so highly structured that you know exactly at what places every value starts and ends, right? Who understands that? Right? So here we save the spaces, the commas. We don't even put the commas. So that's completely arbitrary, and that completely depends on whoever is doing that. That's assuming you have full control over the data and over the sensors like the thermometers and barometers and all the measurement devices. Okay? That's not even JSON or XML. It's just text. Right? Or you could organize your text as key value pairs. It means that you have a special character. Here I use the space, but it doesn't need to be a space, it could be anything, with something on the left and something on the right. So here on the left, I have my years, and on the right, I have my durations. I just need to know what symbol I use for the separation. It could be a comma, a semicolon, a colon, a space, or whatever character you want. So this is a key value approach. We'll see that MapReduce loves that. MapReduce absolutely loves key values. So this is the sort of document that's very easy to feed into MapReduce. Or, surprise, surprise, I can have JSON. So I could have billions or trillions of JSON documents, each on their own line. Not necessarily valid, right? I don't even need a schema or anything for that. In that case, it feels, who feels like here you can have a schema, right? Who could build a schema for that? That's easy, right? Year integer, date, optional. Duration is a time duration, and the content is a string. All right, so it could be JSON lines. Or it could be a binary format, because maybe somebody saw that this is inefficient to have it as JSON, and so they did exactly what I told you. They parsed it into memory, they built a schema, they turned it into a data frame, and they saved it back as Parquet. And Parquet is a binary format, so maybe we have Parquet in HDFS. That's yet another thing you could have. Or could be XML, but I'll get to it. Now, when I told you this is what you have in HDFS, text, CSV, JSON, anything, typically, what you will have in HDFS is not a single file. You're going to have several files. There is a name for that. We call them shards, right? So we have, for example, part 1, part 2, part 3, part 4, and so on. And let's say, just as a rule of thumb, maybe there's 100,000 lines in every one of these files, right? I'll explain to you why we often have these shards and why it's not always in the same file. It has to do with the fact that very often the data we consume was itself produced by somebody else. And so outputting the data in shards is something very, very common in data analysis. And so this is what we have. We have plenty of files on HDFS. Each one of these looks like this, or this, or this, or this, one of these, right? But all organized as shards. So far, so good, right? Now, HDFS is not the only place where we can store data. So of course, that could be S3, but S3 is the same thing. You would just store exactly the same sort of shards and data in there. What about HBase? Maybe people would like to store their data in HBase. And in fact, if they want to store XML, HBase is a pretty good place to store XML. I told you that in HBase, you can commonly have single cells up to 10 megabytes, right, of data. And so you could put some data like this in HBase. So let's say you have billions or trillions of rows, so that would be HBase or relational database management system like PostgreSQL with small values, or XML. So that would be a different use of HBase, where I put an XML document in every cell. And in that case, you see all of these XML documents are not only well-formed, they are also valid against this schema that you see below, right? So you see, year is an integer, date is a date, it's optional, min occurs equals 0 makes it optional. Duration is a duration, canton is a string, and so on. So that tells you the structure of the XML documents. If you can understand this, probably you did the exercises already, and that's great. If you cannot understand this, do not worry, just solve the exercises, right? So read the chapter that explains XML schema and solve the exercises and use XML. But in practice, this is a schema, and we have billions of XML documents that are all valid against that schema stored in cells in HBase, right? All right. And so now that we have this data, text, CSV, JSON, XML, tables, whatever we have, we now want to query it. And the trick that we are going to use is the same trick that we use for the Pokemons. We are going to split, partition, shard the data like this. So I like to call that data is in the shards as a cultural reference, but this is how you remember what's actually happening to all of that data. The idea is actually this. If you zoom out completely on the problem we try to solve, we have a huge data set that is our input, petabytes, exabytes maybe, and we want to query it in order to output another huge data set, petabytes, exabytes. Doesn't have to be, by the way. The output could also be megabytes or gigabytes or even kilobytes if we want, but potentially it can also be petabytes or exabytes. And we want to just write a query that turns the input into the output. So put that way, it's simple, right? But now the key part is to do it efficiently. And so here comes MapReduce. MapReduce was invented at Google. It is an extremely simple and extremely generic approach for doing this efficiently. And the idea is that you split, shard, partition the data, the input data, so you cut it into these splits, and you're also going to generate the output data in splits like this. Now, if I had a Christmas wish list, I would wish for my query to be like this, right? Then you just in parallel process an input split and then you output whatever comes out of that query. You do that on one machine, that on another machine, that on another machine. That would be like the 10 students counting the Pokemon in parallel, right? So you might think, okay, that would be ideal if we had this. But the problem is that if all you can do is query data in parallel, you will not go very far. Because in real life, when you need to query the data, you also need to aggregate the data, to sort the data, and so on, so to do things that you cannot do with this, right? With this, you cannot sort any data. You cannot aggregate any data, right? Because it's kept separated. Every query is in their own silo and on their own machine. There is no communication. So that would be very efficient, but that is not generic. That doesn't solve all the problems. In the real life, this is what you might see, right? What's important to understand here is that in order to produce that partition of the output, you need to read all of that. Maybe everything that is in there is needed to compute what is in here. Imagine some aggregation. Imagine, to take the example you told me earlier, you have some car information and so on, and you want to compute aggregate in Switzerland that what is the number of cars for every canton. If the data is completely randomly distributed, there might be cars from the canton of Zurich all over the place, right? And you want to output right here, Zurich with a number. This is dependent on everything, right? Here you might have the canton of VAT, right? That also depends on everything. There could be VAT information everywhere. Here you might have Geneva, but again, Geneva could be everywhere. So this is a huge spaghetti query, I would say, right? So the complexity looks very quadratic in there in terms of complexity. So it seems bad, right? Because that's not the sort of thing you can parallelize very easily. So could we have some middle grounds that is maybe more generic than that, but also simpler than that? And the answer is yes, because in real life, it looks more like this. It's not fully spaghetti, but also not fully parallel. And so there are parts of your query that are parallel and some other parts of the query that are spaghetti-y, right? That is kind of the real life insight. Sometimes it's like this, sometimes it's like that. And the idea behind MapReduce is to say, let's structure that and have a framework that combines both, but in an orderly fashion. It means that I'm first having a fully parallel part, and then I have the shuffling part where it's all spaghetti and the data just flows around from every machine to every machine. And then again, I have a parallel part, right? And so that part, that initial parallel part is called map. And that second parallel part is called reduce. And we have the shuffling in the middle, but again, that's the one that's commonly forgotten in the name, and we just say MapReduce, okay? Who understands that overview? We map, we shuffle around, and we reduce, right?
So there's a question on Zoom.
Yeah.
Regarding the previous slide on the input partition. So where you had the input, which was partitioned, right? So the question is, do you manually have to make these partitions, or is this basically based on how the files are stored on the hardware?
The partitions, you do have advanced, the expert mode where you can create your own. But in fact, very often the system figures them for you out. And in fact, if your data is on HDFS, then if you think about it, HDFS blocks are a very natural way of having partitions, right? So in fact, what people do when the data is on HDFS is that every HDFS block gives you a partition. It's that simple, right? So imagine that every one of these rectangles separated by the dashed line is an HDFS block, right? And so you need to get data from plenty of blocks to produce an output in there. Does it make sense?
I think so. Otherwise, I will ask a follow-up question.
So that would be the default. But if you're a power user and you disagree with using the HDFS blocks as partitions, then you can change that, right? But then, of course, it's more complicated. You need to know the API for doing that. But as a power user, you can change that behavior, right? But right now, I'm on a high level, right? I'm not looking at HDFS just yet or HBase. I will get to that, how it actually physically is implemented. Right now, I have a very generic view. These rectangles could also be the bags with the papers that I distributed to the students, right? It doesn't need to be a file system or even a computer, right? That's a conceptual view, mathematical view, right? All right. And how did I produce these partitions? Well, I did it at home, right? I just took the papers and randomly put them into bags, and that gave me my partitions. So in the case of the Pokemons. All right, I just tried to do it a bit evenly, that there were more or less the same number of Pokemons in every bag. All right, so that is MapReduce. It is both simple conceptually and very generic. And that could be something surprising, that something that simple can actually solve many problems. To name a few, you can use this to index the internet and build a Google. Really, like this is how you build a Google. The input data is the entire internet, all of the web pages, and what's happening with Google and Yahoo and Bing, and they actually do something like this. And what you get as the output is an index that you can use when somebody types in a text box a certain query. Then you can efficiently look at the output data to recover the web page that it came from. So you can literally build a Google with this. Another thing you can do is matrix multiplication, machine learning. You can implement machine learning algorithms also on top of structures like this. This is how generic and powerful it is. right? Even though it looks very simple conceptually. So this is really a big deal. And 20 years ago, that became a big buzzword. Like everybody was MapReduce, 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 right? That was the blockchain of the time. All right, so this is MapReduce. Of course, I'll take the time to go through it and tell you how it's implemented and so on, but conceptually, this is the most important slide of MapReduce. This is what you should have in mind as this is MapReduce. Right. All right, now let's be a bit more specific. What is shuffled? I'm going to call it intermediate data. Intermediate data. The intermediate data are the Pokemon strips that the mapping students hand over to the reducing students. In intermediate data, because it only contains the counts of one bag of Pokemons, right? It's not the final counts, so we call it intermediate data. The intermediate data will be thrown away at the end, right? It's just there for the computations, then we throw it away. What we really keep is the output data. So you see, we have three kinds of data: the input data, the intermediate data that gets shuffled around, and the output data. Right? Now, one more thing. MapReduce wants all of these to be collections of key-value pairs. The input data has to be a collection of key-value pairs, the intermediate data has to be a collection of key-value pairs, and the output data has to be a collection of key-value pairs. If you think of the Pokemons, the key was the Pokemon and the value was the number, right? You can visualize it in this way. Now you might say, okay, yes, but the input was not key-value pairs, it was actual Pokemons, right? But you can easily turn them into key-value pairs, right? You could, for example, put a dummy key, right? Every Pokemon you associate with the key whatever, right? And then the Pokemon is the value, and that works, right? So you can turn everything into a key-value pair if you want. So it's the way I think about it is, you know, when you have a hammer, then everything in the world looks like a nail, right? And that's a bit like the MapReduce view, right? Everything in the world is a key-value pair or is a collection of key-value pairs. All right, so key-value pairs, key-value pairs, key-value pairs. However, the kind of keys and the kinds of values, more exactly the type of the keys and the type of the values, need not be the same in these three phases. You could have in the input phase, in the case of the Pokemons, the key type was whatever. You just put whatever you want just to have a key, but it doesn't matter. And then the Pokemon. In the case of the Pokemon, that was the Pokemon, that was the intermediate count. And in the case of the Pokemon, the key here was a Pokemon, and that was my final count, right? So it turns out that for the Pokemons, we have the same types here. It was in both cases a Pokemon with an intermediate count or a final count. Very often, that's the case. Sometimes it might be different, but in 80% of the cases, we in fact have the same type of keys for intermediates and outputs. Who is with me? All right. So now I'm going to have a walkthrough of a whole MapReduce query from a logical perspective. I'm not looking at HDFS or machines or whatever. I'm just looking at the high level, the math of what's going on. So I start with my collection of key values, because I told you everything is a collection of key values. So let's say I have billions or trillions of key values. So the first thing I do is that I read them, right? So I have my collection of key values, and I just read my key values. This is a key value, 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 look, all the values, right? That's part one. Part two is I take each key value, so this is one of them, but I would have to do to all of them. Each key value, one at a time, gets mapped to 0, 1, 2, or more intermediate key values. 0, 1, 2, or more. Can be none at all, can be just one, can be two, can be 10, can be thousands, any you want. That is my mapping function. Who decides on the mapping function? You. That is the user. That's provided by the user. Can be absolutely anything as long as it's a function that takes one key value and outputs 0, 1, or more intermediate key values. And that function is going to be different depending on whether you want to build a Google or implement a matrix multiplication for machine learning, right? It's different map functions. But as far as MapReduce is concerned, it's just a mathematical function. Next, I'm going to do that not just for one key value, but for every key value, I'm going to call that map function. So you can see I told you 0, 1, or more. So here we have 2, here we have 1, here we have none, here we have 1, here we have none, here we have 2, right? So just to be fully generic. Next, I'm going to take all of these intermediate key values all together. I assemble them back. It's conceptual, right? That's mathematical. In my mind, now I have this gigantic collection of intermediate key values that I just concatenated from what I got from the earlier phase. The next thing I'm going to do is, you realize here it's not sorted, right? I have key 1 here and here. I have key 3 here and here. Let's sort it. I'm sorting it, and I have all the key 1s in here, then all the key 2s, then all the key 3s, right? So I sort it. After having sorted it, I partition it by key, meaning that all the key 1s, I take them in a single batch in here, then key 2, another one, then key 3, another one, right? So far, so good. Then, for every one of these groups of intermediate key value pairs that all have the same key, right? What's very important is that they all have the same key, and it's everything that has that key, right? I have all the key 1s are in there. There's no key 1s anywhere else. They're all in there. That's complete. Then I have my reduce function that takes as input an intermediate collection of key values with all the same key, and all of them with that key, which produces, guess what, 0, 1, 2, or more final key values. Right. So if I do it, in parallel, do I have? Yes, I have a parallel here. So I have here an intermediate collection key 1 that produces this, here produces that, here produces that. Now, I told you 0, 1, 2, or more. Indeed, in many cases, it's going to be exactly 1. Right? So very, very often, the reduce function produces exactly 1 key. Doesn't have to be, could be 0, could be more, but that's the reason why I put a very common example in here where it's just 1. Now, coming back here, I told you very often the types for the intermediate and final outputs are the same. So very often, the reduce function keeps key A. It basically takes key A, keeps it, and the value you have here is very often some aggregation of these values. Could be the count, the sum, the average, the max, the mean, whatever. So it's a very, very common pattern that you keep the same key and you aggregate the values. 80% of the cases, it's like this. And in some other cases, it's not like this. Then it's just a more generic thing. And again, I repeat, yes?
There's a question.
Yeah.
So in the original map phase, you have these initial values, and then you have this intermediate, keys. You have these initial keys and these intermediate keys. And the question is, how do you decide what the intermediate key should be?
The user. Yeah, it's entirely up to the user. You, as the user of MapReduce, define the types of keys and values you process. You define your map function, and you define your reduce function. That is the job of the user of MapReduce to do that. And you're going to do it differently depending on if you want to index the web, or if you want to do machine learning, or if you want to count the words that Sir Arthur Conan Doyle wrote. It really depends on your use case. But again, I repeat, it's you as the user of MapReduce who makes that decision. Yeah. Does it make sense?
Yes, I think it makes sense. So there's a short follow-up question. If you could give an example of such a mapping phase.
I will have examples.
Sorry?
I will have examples.
Yeah, okay.
Yeah, plenty of them. Yeah. So that I will come to it. Yeah.
Thank you.
No worries at all. Here is just the logic of that. Okay. All right. Okay. So the reduce function also provided by the user, you, me, so whoever uses MapReduce. And very commonly, we just aggregate the values and keep the key. In general, you can have 0, 1, or more outputs, but here in 99% of the cases, it's going to be just exactly 1 value. And looks like this. And so that's the summary, right? This is my input collection. That's the intermediate key values I get after applying my map function. I shuffle around, sort, partition, and so on. Then I call my reduce function on every distinct intermediate key, on the group of key values with that key, and then I have my output. That is MapReduce. Who is with me? Right, very good. So now I'm going to start telling you more about the architecture of MapReduce, the way it's done. So the data, so the input data, could come from HDFS. It could come from your local file system. You can also execute MapReduce on your laptop, right, on your local data, and it's just going to spread over the course of your laptop. Could be on S3, could be on Azure Blob Storage, could be on HBase, could be on a relational database. So there's many, many possible storage layers. So this is really something universal here. And so typically you can process terabytes of data with thousands or even 10,000s of nodes that process that data, especially for the map and the reduce. And so the architecture looks like this, and that shouldn't be a surprise. We've seen that before. We've seen it in HDFS, name node, data node, data node, data node, data node. We've seen it in HBase, HMaster, region server, region server, region server, region server. So that's HDFS, that's HBase, and that is MapReduce, Hadoop MapReduce. So we just need names for that. So job tracker is the name of the process that centralizes everything, and task tracker is the name of the process that executes on every working node. These are the same machines, right? So the name nodes, the HMaster, and the job tracker are three processes on the same machine. And the data node, the region server, and the task tracker all run together on the same working machines, right? These are the same machines in there, just different processes. Okay? And it's very important that it's the same machines, because that is absolutely fundamental to the way that MapReduce works, is that the data is on the same machine on which you execute the map function. You read it directly from where you are. That is why it's very efficient. So that's called also, that's known as bring the query to the data, right? The data is already stored in HDFS. It's already stored as blocks on the disks of all of these machines. So if you want to map the data, just do it on the same machines, right? It's that simple. So we bring the query to the data, and we are going to execute the map function on the same machines as the data nodes, right where the data is. So I told you now, I've already told you that a natural split or partition for the input data is to just take the HDFS blocks, right? So we are just going to say we have a specific HDFS file or several HDFS files. Every block gives us a split, a partition of the inputs. Right? So I marked some of them. I didn't put replicas in there to not, because of course, when you have replicas, you can choose. If a block is stored 3 times, then you can execute it on any of the 3 machines, right? And that you can figure out efficiently. So I didn't put the replicates in there, but I have the splits of MapReduce that are going to be taken. And now I have on every machine my cores, my computer cores, my CPU cores that are going to be assigned to some mapping on some reducing, right? And of course, we start with the mapping. And that's going to read the data locally, because there is a copy of the replica on the machine on which you execute the mapping function. Sometimes it doesn't work. Most of the time it's local. We'll see, I'll come back to it later. In some cases, it might be that that machine, for example, that's mostly processing that split, might need to read remotely from another machine, right? It's not perfect. It's not in 100% of the case that it's local. Sometimes you need to read remotely, and that's okay, because HDFS allows you to read remotely, right? Who is with me? Right, very good. So what happens is we have the map function that is executed on the CPU, reading from the local splits, and we create the intermediate key value pairs, right? And at some point, I'm going to have a lot of key value pairs that start accumulating in my memory, all of the intermediate key value pairs that I'm created, the Pokemon strips. And at some point, the memory is full. What do we do when the memory is full? Or otherly said, does that ring a bell? We already saw the memory full in HBase, right? What did we do when the memory was full in HBase? we flushed, and we do exactly the same thing. It's just not called flush, it's called spilled, but this is the same thing, right? We spill to disk. It's like the flush in HBase. We just put it on disk. And we also have the compaction that also exists. After you have flushed many times, you can also compact it to some unique files. So that I'm not going to come back on that because we covered it in HBase, right? This idea of flushing to disk and compacting and so on. And so what happens is that once that has been done and the data has been flushed and compacted to disk, the shuffling happens. And it means that every machine is connected to every other machine and requests the key value pairs they need. It's like Alice who is collecting all the Pikachus from all the mapping students. So this is the huge mess. This is the shuffling. The shuffling is done over HTTP. It means that a machine that is supposed to reduce, technically all the machines, is going to connect via HTTP to every other machine and say, please give me all the key value pairs that I'm responsible with. Imagine that that machine is responsible for Pikachu, is going to connect to every machine asking for all the Pikachus. Right? This is basically what's going on. So that's the shuffling phase. And the key value pairs are all handed over and land on that machine. And since this is done by every machine, then you get this huge shuffling all over the place in the cluster. Then you have the reducing phase. So we use the CPUs, the cores that are used for reducing. And that's going to write back to HDFS. So every single slot here, every single core is going to write back one file to HDFS. And that's where they come from, part 1, part 2, part 3, and so on. This is because they're all done by separately on all the machines. Who is with me? All right. I would like, because of the question you asked, instead of doing it next week, I just want to give you an example just before we go. So I'm going to go, sorry if it flickers, I'm going to go forward just to the part I need to answer the question that was asked. So just give me a few seconds. Just need to go to the example. Yes, exactly. So you asked me for an example. Here's an example. Imagine that your input is text. You have all the Shakespeare or Sherlock Holmes on the HDFS. So the first thing you need to do is turn it into key value pairs. We do it like the Pokemons, meaning that we do dummy keys. So every line of text gives me a key value pair, and here I just put in the key whatever I want. It's totally useless. So let's put an offset. 18 just means that it's in position 18 in the text file. This is in position 27. It's just counting characters. It doesn't matter, right? This is just something dummy that we put in there, and the text is in the values. Now you agree I have a collection of key values, right? After doing that. That's great because MapReduce needs a collection of key values. So that's it. And now I'm going to have a map function that counts the words. For example, here I have once lorem, once ipsum, $1. So I'm creating my pairs in here. Here I have Sit and Ahmet, 1, 1, and so on, right? So I create, that's my map function, right? That maps this to this, very similar to the Pokemons, actually. And then my reduce function is going to compute the count or the sum. If it's only ones, then count or sum is the same. I count, right, or do the sum, and I have my output pair. Who agrees that this is counting how many times every word appears in my text? You agree, right? It's like the Pokemons. I count it. So this is a concrete example. And this is one of many, many, many examples. The limit is just your imagination, what you want to do. You can freely choose your types of key and value. You can freely choose your map function. You can freely choose your reduce function. Entirely up to you. Extremely simple, extremely powerful. Does it answer the question on Zoom as an example?
I'm pretty sure it does.
Yep. All right. So I'm going to let you go. I just want to check that everybody followed. So just to make sure. Probably need to refresh the page. Hopefully it doesn't crash. Yes, that's great. And where are we? This is April 8th. Okay, just checking.
So maybe while this vote is going on, there's another question on Zoom. So the question is regarding this architecture you showed for job tracker, etc. And the question is, so in each job, I think it was job tracker, there are exactly 3 files in the end. Why exactly 3 files in the end?
Oh, it doesn't have to be. It's can be any number. It's basically every basically the idea is that let me use the students and Pokemons. I had 8 students who were responsible for counting the final numbers, right? Every one of these students was responsible for 1 Pokemon or more. Some of the students had 2 Pokemons, right? In fact, it's arbitrary. You could have several Pokemons for every reducer students. The idea is that every one of these reducer students writes back 1 file. That's the idea. Okay, does it answer the question?
Okay, I think I misunderstood the question. Sorry. So the exact question was, in the figure you showed, in the end, there was 3 files with the same color. So the question is, why do you have 3 replicas? Why do you have 3 times the same file?
Oh, let's see. Let me go back to where we were. That was something like here, right? Can you guide me on the slide?
Maybe you can go through them. Maybe there is one slide where the colors are the same.
Oh, same. Oh, yes, you mean the colors? No, it's totally arbitrary. Consider that all the colors are different. It's what I wrote here, only 1 replica shown per block. So there are no replicas of the same blocks in here, right? Every block is processed just once. You don't process different replicas of the same block at the same time. It's only 1 replica that's going to be processed. Yeah, just waiting for a confirmation that it answers the question.
I think they're referring to the next slide with the results.
Oh, the next slide. Yeah.
Maybe one more next.
The results. Oh, no, these are also different colors. It's not the same. This is yet other new blocks that you write. Maybe I will change the colors to make it even clearer, because that's the output. It's a completely new file, completely new blocks.
Can you go one further?
Yeah.
One further? One further? Okay. So the user said there's some slides where all are brown. I think that's the one.
Oh, no, I could have put colors in there as well. Did you want me to put colors? I can put colors. I'll do that. Yeah.
Okay, I think.
Yeah, I just put everything in brown, but it could be in any color. Yeah.
So the different files, just the colors are the same.
Yes, exactly. Yeah, files. That might have been confusing. Yeah, I'll just put colors in there, and then it takes care of the confusion.
Yeah. Okay. Right. Thank you.
All right, but it's very good that you ask clarifying questions, because sometimes it might not always be clear. So this is great, more than 80%. I really recommend read the book, read the chapter on MapReduce in the book, solve the exercises, make yourself familiar with JSON schema, XML schema, play with it, and of course you'll play with MapReduce as well a bit later. And don't worry, I'm not done with MapReduce. I will still go through it again and again and again, give you different perspective and make sure that we understand deeper how it's all working. So do not worry, we'll continue next week with even more explanations. All right, if you have any questions, write us emails, write on the forum, ask each other. Thank you very much, everybody. Enjoy the exercises, and I'll see you next week for the lecture. And no exercises next week, but there's still a lecture next week. Yeah. Thank you very much. Goodbye. Thank you, Florian, for moderating.